mrcad, multimodal refinement of computer-aided designs. There's a need for refinement when interacting with AI models. For instance, let's say you ask it to draw you a robot, and the robot you have in mind is the blue one. It will create you a robot. It looks good, but it's not quite like the robot, the blue one you have in mind. So what do? You ask the AI to refine. You ask it, can you make the eyes really far apart? But refinement is difficult for existing language models. It often will not follow your refinement instruction. In this talk, we'll look at the difference between generation versus refinement. In generation, you start with nothing, such as the empty canvas. After some instruction, the AI creates you an artifact. However, in refinement, there is already an artifact, perhaps already made by the AI, and the instruction is used to alter the artifact into something different. And this refinement may occur for multiple iterations, one after another, forming a sequence of refinement steps. The mrcad dataset is a dataset studying the effect of refinement on AI models. We choose the domain of CAD, or computer-aided design, because in design, we often have many versions of refinement. These refinements are very tedious, carried out manually by a human with a mouse and keyboard. So we ask, is it possible to make an AI agent that humans communicate with intuitively using language or some other modalities, and the robot controls the mouse and the keyboard agentically to do refinement on the design? Instead of real CAD, we choose the domain of simplified CAD, and you really should think of it like PowerPoint. You could make lines, arcs, and circles, you can move them around, and you can delete them. The game we study for refinement is a two-player game. There is a designer and there is a maker. The designer is given a target design that only the designer knows, and the maker does not know this target design. The designer will give multimodal instructions to the maker. So here the designer draws something in red, and they also add a natural language instruction to complement. Here he says, just straight lines, all the mini lines are the same length. The maker takes this multimodal instruction and executes it to create a CAD on the canvas. This current CAD shown on the right is not quite like the target. So the designer will give additional instruction to refine the CAD. Here the designer drew some additional red lines, again with some additional natural language instructions. The maker again interpret and execute this instruction, and now the current CAD look much more like the target than before. The designer might follow up with another round of refinement, and the maker was able to create or recreate the target design that's very close to the original. And we have seen 3 rounds. So this is a trajectory between the designer and the maker in 3 rounds of instruction and execution pairs. And we stop the game if the final execution produces a design that's sufficiently close to the target. To measure distance, we use chamfer distance. Essentially, it's a distance measured between the set of points sampled from each design. And here's the dataset statistics. We play these multimodal iterative refinement games, and we played 6,000-ish of these games, and our dataset contains all full trajectories of these games. Of these about 6,000 games, there are 15,000 rounds, consisting of 6,000-ish generation round, which is the first round from the empty canvas to the initial design, and about 9,000 refinement round, which is round 2 onward, taking an existing design and changing it to a different design. These games are played between about 1,000 dyads, which are 1,000 pairs of human participants, and in total we try to reconstruct about 3,000 distinct CAD designs. Of these 3,000 CAD designs, we have about 2,000 CAD designs in the coverage set. For the coverage set, there are 1 or 2 reconstructions of the design. There is a dense set consisting of about 700 designs, each reconstructed 3 or 4 times. And there is a very dense set consisting of 27 designs, each reconstructed successfully 30 times. We imagine the coverage set will be good for training or fine-tuning some model. We imagine the dense set will be useful for evaluating these models. And we imagine the very dense set to be very useful for cognitive analysis, because we capture the full, or try to capture the full distribution of human strategies of reconstructing these designs. Evaluation of VLMs on mrcad. So we're interested in 2 kinds of evaluation. One for the ability to generate. So here on the left is a generation task, and we evaluate human performance versus machine. On the right is a refinement task. So after the initial round and several back and forth, we ask, can the human follow the instruction for refinement versus how well can the machine follow the instruction for refinement? And here's the result. The top line, higher the better. The top line, the blue one, human, is very good. And human is consistently able to make the current design more and more like the target in all rounds. What we find is that major VLMs does okay at making the initial guess for generation, but for every subsequent round in refinement, VLM actually made things worse in refinement. So here are some examples of failed refinement. Here is an instruction on the left asking it to make the circles concentric, along with, if you look at the red marks on the side, which is to remove the little line segments between the second and the third ring. A human is able to correctly interpret this instruction and remove the lines and center the circles. And GPT-4 did, I don't know what it is, but it's not the right. And here's another failed refinement instruction where you are bringing the bit at the top. So here is a bit at the top to line up with the top of the B. So the idea is you take the B shape on the bottom and line it horizontally with this noodle shape on top. The human is able to align the top part of these two shapes, and GPT-4 again did something that I cannot explain. And so why do VLM perform very badly at refinement? Here are some reasons. The first reason is that generation is very different from refinement. So for generation in our dataset, we start with empty canvas. Participants tend to have full drawing for the entire design, and the language used tend to have more nouns. But for refinement, the canvas is not empty, and the drawings are a lot more partial. If you look at the red lines here, they are not the entire drawing in the entire design. And then they use more verb in the language instruction. If we take a look at the aggregate, generation and refinement are also very different. So if you look at the left plot, on the first round for generation, almost all participants use some drawing. So it's either all drawing, which is red, or drawing with text, which is purple. But as we go into refinement, the participant began to use more text and only text. So these are the blue. So as you can see, there's more blue over time, meaning as we go more into refinement round, the participant tend to use more text only. And the text the participant use are also very different. On the right plot, you see for the generation round, the first round, there are more nouns. And for the later rounds, refinement, there are more verbs and more imperative verbs asking the other participant to modify something of the existing design. There are these things, what we call imperative drawing, which is drawing used to do things. So on the left is a declarative drawing, which is to just ask the other participant to draw the red line where it is shown. But on the right-hand side, we see there are arrows, and there is this bracket shape. So this bracket shape indicates a part of the drawing that the other participant should pay attention to, and the arrow says that you should move this part to the right. And it's complemented with a natural language instruction, move the right almost all the way to the edge. Lastly, there is a language of multimodal instruction for refinement that is very poorly understood by existing VLMs and poorly understood in general, I think. So here on the left, we can see the usage of arrows, and on the right, the usage of these X marks. And the instruction says, make the part marked by X more rectangular rather than circular. So we know very little about how to ground these multimodal refinement instructions. So in conclusion, mrcad is a collection of things. It's a reference, it's a benchmark, and it's a dataset. And you could use this to, for instance, evaluate VLM models, build cognitive models of human communication, and to study multi-turn instruction following and multimodal instruction grounding. Thank you. Here's us in nice and photo form. And finally, you can scan the QR code or follow the link for all of the analysis code and the full data set. It's all on this page. Thank you.